Good morning everyone. Welcome to this video lecture series on matrices and calculus, course code MA3122. Myself Mohan, working as a assistant professor in the Department of Mathematics at SRM Engineering College located in Katakulathur, Chennai. In this video lecture, we will explore the fundamental concepts in linear algebra and calculus that form the foundation for advanced engineering mathematics. These topics are essential for engineering students and will help you understand concepts in signal processing, control system, and structural analysis. Today's session focuses on matrices and their properties, including eigenvalues and eigenvectors, reduction from the quadratic form to canonical form. These concepts that have real-world applications in physics, engineering, and data analysis. So let's start with the fundamental classification of matrices. A matrix is a rectangular array of numbers arranged in rows and columns. So we'll see the types of matrices include real matrix. So real matrix, all the elements in the matrix are real numbers. And the square matrix. The square matrix in which the number of rows equal to the number of columns is called the square matrix. Row matrix. A matrix having the only one row and any number of columns. A matrix of order 1 into n is called a row matrix. Column matrix, a matrix having only one column and any number of rows. A matrix of order m cross 1 is called the column matrix. Null matrix, which is each element is 0 is called the null matrix. Diagonal matrix, a square matrix in which all non-diagonal elements are 0 is called a diagonal matrix. Scalar matrix, a diagonal matrix in which all the diagonal elements are equal to scalar, say k, is called a scalar matrix. Unit matrix is nothing but a scalar matrix in which each diagonal element is 1 is called a unit matrix. Upper triangular matrix, a square matrix in which all the elements below the principal diagonal are 0 is called an upper triangular matrix, and the lower triangular matrix which all the elements above the principal diagonal are 0 is called the lower triangular matrix. So finally, equal matrices. Two matrices A and B are said to be equal if and only if they have the same order and their corresponding elements are equal. Okay, so now we are going to see the characteristic equation. So now let's move to one of the most important concepts in linear algebra, eigenvalues and eigenvectors. Before that, we should know the concept of characteristic equation. If A is any square matrix of order n, we can form the matrix A minus lambda I, where I is the nth order unit matrix. Here lambda represents the eigenvalue, I is the identity matrix, A is the square matrix, determinant is denotes the determinant of the given matrix form. Next, eigenvectors. Eigenvectors is a consider the linear transformation y is equal to ax, which transforms the column vector x into the column vector y. We often require to find those vectors x which transform into a scalar multiples of themselves. Let capital X be such a vector which transforms x by the transformation. Then y is equal to lambda x. So finally, we are concluding a minus lambda I of x is equal to 0. This is the form of I. Here capital X denotes the eigenvectors. So let's move to the next topic, properties of eigenvalues. This most important topics. It covers the part A questions. The first property is the sum of eigenvalues of a matrix is the sum of the elements of principal diagonal of the given matrix. Property number 2, the product of the eigenvalues of a matrix is equal to its determinant value. Property number 3, if lambda is an eigenvalue of a matrix A, then 1 by lambda is the eigenvalue of A inverse. Similarly, we can define the other properties like if lambda 1, lambda 2 and so on, lambda n are the eigenvalues of A, we can define the following three conditions. K lambda 1, K lambda 2 up to K lambda n are the eigenvalues of the matrix Ka, where K is a non-zero scalar. Next, the subdivision 2. The same, if lambda 1, lambda 2 up to lambda n are the eigenvalues of A, then 1 by lambda 1, 1 by lambda 2 and so on 1 by lambda n are the eigenvalues of A inverse. Next one, lambda 1, lambda 2 up to lambda n are the eigenvalues of A, then lambda 1 power p, lambda 2 power p up to lambda n power p are eigenvalues of A power p. So here we have the proofs of these properties. Okay, so let's jump to the problems based on the properties. The sum of the eigenvalues. So we have to find the sum of the eigenvalues of A. It is equal to the sum of its diagonal elements. So what is the given matrix? So take the eigenvalues of the uh, eigenvalues of the two eigenvalues of the matrix are equal to 1 each. Find the third eigenvalue. So let A be the third eigenvalue of A. Since sum of the eigenvalues is equal to sum of the diagonal elements, by this property 1 plus 1 plus A is equal to 2 plus 3 plus 2. So we can find the value of A, that is third eigenvalue is 5. Next problem, the product of two eigenvalues of the matrix capital A is 16. Find the third eigenvalue. So for this problem we can use the property the product of eigenvalues. We know that product of eigenvalues is equal to determinant of A. So from this problem the determinant of A value is 16. Determinant of A value is 32. So the product of the two eigenvalues is 16 and the unknown eigenvalue we consider small a. So 16a equal to 32, A value is 2. Similarly, we can find the other problems, solve the other problems. Next, we are moving to the finding the eigenvalues and eigenvectors of a matrix. So first, what is the first step to find the eigenvalues? To to frame the characteristic equation using this equation, determinant of A minus lambda I is equal to 0. So A is the given matrix. So from the determinant of A minus lambda I is equal to 0, we got a cubic polynomial in terms of lambda, that is minus lambda cube plus 18 lambda square minus 45 lambda is equal to 0. Solving this polynomial, we got the values lambda equal to 0, 3, 15. So these are the eigenvalues 0, 3, 15 for this problem. Next, we are going to find the eigenvectors corresponding to the lambda value 0. So already we know that what is the format of finding the eigenvector. A minus lambda I into x is equal to 0. Here x is represented by x1, x2, x3. This is the eigenvector. So we are using the A matrix and the x1 is x1, x2, x3 is equal to is the column format 0, 0, 0. So using the matrix multiplication, we got the linear equation like 8x1 minus 6x2 plus 2x3 is equal to 0. Similarly, we got the three equation. On solving these three equation by cross multiplication method, we got the values of capital X1 is equal to 1, 2, 2. Similarly, we can find the other eigenvectors for the corresponding eigenvalues. So for lambda is equal to 3, we can find the x2, that is second eigenvector, that is 2, 1, minus 2. Similarly, we can find the third eigenvector, that is 2, minus 2, 1. Similarly, we can find the other problems, solve the other problems. Next, we are moving to the topic, that is Cayley-Hamilton theorem. So it is also very important theorem in this matrix chapter. Every square matrix satisfies its own characteristic equation. This is the statement of the Cayley-Hamilton theorem. So for exam point of view, they are asking the 8 more questions like verify Cayley-Hamilton theorem for the given matrix. So how to verify the Cayley-Hamilton theorem? Let's see. So the given matrix is capital A is equal to 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. They are asking verify Cayley-Hamilton and compute A inverse value. So in the plus 2 or school level, we can use formula A inverse equal to 1 by determinant A into adjoint A. This is a very well known formula. But here we are using the Cayley-Hamilton theorem for finding the A inverse and A power 4 like that. So before that, in the same way, that is the finding the characteristic equation of A. So what is the characteristic equation of this matrix? That is lambda cube minus 6 lambda square plus 9 lambda minus 4 is equal to 0. So from that, we can change the lambda by capital A. So the equation is changed like a cube minus 6a square plus 9a minus 4i is equal to 0. Now we can find the a cube value. Before that, we should find the a square value. A square is nothing, a into a, and also find the a cube value. Then substitute in the LHS a cube minus 6a square plus 9a minus 4i. The answer will be null matrix, that is 0. This verifies the Cayley-Hamilton theorem. And another one question is there, that is finding the A inverse. How to find the A inverse? It is very simple. Consider the previous equation, the characteristic equation A cube minus 6A square plus 9A minus 4 I equal to 0. We can pre-multiply by A inverse. We got the reduced equation is A square minus 6A plus 9A minus 4A inverse is equal to 0. From that, we can separate the A inverse value, that is 4A inverse equal to A square minus 6A plus 9A. So already previous part we got the A square value. So substitute the A square, A and I matrices value here. We can find the A inverse 1 by 4, 3, 1, minus 1, 1, 3, 1, minus 1, 1, 3. The problem is solved. Similarly, we can find we can do all the problems, verify Cayley-Hamilton theorem, and find the A inverse diagonalization value. Okay, so that is the similarity transformation. Orthogonal transformation of a symmetric matrix into a diagonal form. A square matrix A with real elements is said to be orthogonal if A A inverse is equal to I is equal to A inverse into A. So diagonalization by orthogonal transformation possible only for a real symmetric matrix. Using the formula capital D is equal to n transpose an, and the way to find the diagonal matrix for the given matrix A. Okay, we can see the one diagonalization problem. Diagonalize the matrix capital A is equal to 2 0 4 0 6 0 4 0 2 by means of an orthogonal transformation. The first step we are going to find the characteristic equation of the capital A and also find the eigenvalues. So from solving the characteristic equation, so we got the eigenvalues minus 2 6 6. Using the eigenvector method, find we are going to find the first eigenvector and the second eigenvector and the third eigenvector. So find the model matrix and also find the capital N, that is normalized model matrix. Okay. So normalized model matrix, that is capital N is equal to 1 by root 2, 0 minus 1 by root 2, 1 by root 2, 0, 1 by root 2, 0, 1, 0. Already we said the diagonal formula is D is equal to N transpose AN. So we know the matrix multiplication method. By using this method, we can find the capital D, that is minus 2, 0, 0, 0, 6, 0, 0, 0, 6, which is required diagonal matrix. So in this chapter, the final concept is quadratic forms. So quadratic forms, we can change the quadratic forms to canonical form. So these are the how to find the quadratic form to canonical form by using the reduction orthogonal transformation. Okay, so here we are going to find one problem. Yes, reduce the 8x square plus 7y square plus 3z square minus 12xy plus 4xz minus 8yz into canonical form by orthogonal reduction. The matrix of a quadratic form is A is equal to 8 minus 6 2 minus 6 7 minus 4 2 minus 4 3. Hence we can find the characteristic roots of a given by determinant of a minus lambda a is equal to 0, that is 8 minus lambda minus 6 2 minus 6 7 minus lambda minus 4 2 minus 4 3 minus lambda is equal to 0. Hence we can find the eigenvalues. Lambda is equal to 0 3 15. Next we are going to find the eigenvectors. For the first eigenvalue lambda equal to 0, by the known cross multiplication method, x1 is equal to 1 2 2. For the lambda is equal to 3 value, we can find the another eigenvector, that is capital X2 equal to 2 minus 1 minus 2. For lambda is equal to 15, the third eigenvector will be 2 minus 2 1. Then form the normalized model matrix, that is n. We can find the capital N, that is 2 by 3 1 by 3 minus 2 by 3 1 by 3 2 by 3 2 by 3 2 by 3 minus 2 by 3 1 by 3. We know the formula for capital D, that is N transpose AN. By matrix multiplication, we got the final answer, that is the diagonal matrix 3 0 0 0 0 0 0 0 15. Now the diagonalization process is over. This question is required the canonical form. So how to find the canonical form? It is very easy. You can find the canonical form by using the formula y transpose capital D y. So y is nothing but y1, y2, y3 in the row or column format. So from this slide, we can see the y transpose is y1, y2, y3. Capital D is the answer of the diagonalization process 300000015. Y is eigenvector form y1, y2, y3. So using matrix multiplication, we got the answer 3y1 squares plus 0y2 square plus 15y3 square, that is required canonical form. So by this way we can find the other problems and solve the all the problems. Thank you.